Okay, continuing on with our theme from the previous video, how to go against electronic preferences. Um, we began this chapter with what most books consider to be the most fundamental addition reaction, which is HX or HBr in this case. And we get, of course, the Moore substituted halide. Well, again, much like the toddler that most chemists really are deep inside, what if I wanted the other one? Now, in this case, I don't have an easy way to reverse polarity the way I did with the oxygen. I don't have an easy surrogate I can work with here. I don't have anything that works quite that simply. So what I'm going to have to do actually is visit, at least briefly, the wonderful world of radical processes. Really a different way of looking at reactions entirely. Thankfully, not all that common, but necessary here to be able to do this reversal of polarity of what we would normally get is our Moore substituted alkyl halide and allow us to get the exact opposite regiochemistry. So, to begin, radical reactions typically have three different parts. 1. Initiation. This is only going to be a very small amount of the process, and I'm going to basically have a single step where I start out with no radicals. And in that single step, I'm going to end up with 2. So, in this case, the conditions we're going to use are still going to be HBr, but now we're going to have a peroxide present, so something like this. And that's going to get us what we want, our halogen on the wrong carbon, or the uncommon carbon that we couldn't get in a purely simple HBr addition. So in this case, the initiation generally is that peroxide. So I'm going to have something like this. And either with heat or with ultraviolet light, I'm going to end up doing a homolytic bond cleavage here. Again, radical reactions only use a single-headed arrow, so-called fishhook arrow. What I get out of that is 2 molecules of this, where I have an unpaired electron. Now, I haven't drawn the lone pairs here. I could if I need to. We're not going to use them, but they're still there. Notice this oxygen is not an octet rule violation. Sorry, it is an octet rule violation, but it still has no formal charge because it still can claim 6 electrons, half the bonding electrons and all of the non-bonding electrons, so a total of 6, which is its atomic state. Second step is typically the most complex for radical processes. It's called propagation. Propagation is where we tend to see a cycle. So something that's used up in one step will be regenerated in the next. There are going to be more than one propagation step in every radical process. A very small amount of it will involve this initiator. This is typically present, our initiator is typically present in less than 5%. So there's a very small amount of it. It's just to get things started. One way of thinking about it is it's just like the spark to start your car. Once you've turned the key and the car starts, you don't have to sit there and hold the key anymore. It's started. It doesn't need your help anymore to keep the engine running as long as there's fuel. So that's pretty much what this is. This is the spark. Without it, you're not going anywhere, but you don't need much of it to get things started, and then the reaction will take care of itself. So our first propagation step is going to basically be that initiator and HBr. Now, normally, we're going to see hydrogens not be a part. We're not going to see hydrogens floating around as individual radicals. They typically get used up by something else. So in this case, this is what a radical bond formation looks like. I'm bringing together 2 of them, and the HBr bond is going to split. Half of it's going that way, the other's going the other half. So here's what I'm getting out of my oxide radical, my oxygen radical. It's going to give me an alcohol. Stable byproduct, basically gets out of the way at this point. My other byproduct, or the useful piece that I'm going to need, is that this is how I generate the bromine radical that I'm going to use for the next step. Second step. Now we're going to end up reacting with the alkene. So I still have those loosely bound pi electrons. Generally we use them one at a time, but generally we use them two at a time, but there's no reason that we can't do it the other way. And, well, I'm about to have the same question I had with the cation. My cation question when I showed this reaction without peroxides, the first video on reactions, was I had this possibility versus this one. And the answer was, this is our more stable cation on the left, where I've got the more substituted cation that's stabilized. The question here is going to be, what's a radical look like? Is it a half-filled orbital? Is it a half-empty orbital? Because our resonance version of an alkene, we basically said the less substituted carbon is going to look like this. So here's what we're going to see, is that if I drew that unofficial resonance structure, well, this is how we can think about it. That I have a cation on the more substituted carbon, I have an anion on the less. So the question is, what's a half version of that look like? Does a single electron behave like an empty orbital, meaning like a cation, or like a filled orbital, meaning like an anion? And the real question is how it behaves in terms of stabilization. What stabilizes the cation here is hyperconjugation. That is helping out the fact that this is not a filled orbital by hyperconjugation. Well, the same thing is happening with a half-filled orbital. So this is a pessimistic approach. The glass is half empty. The orbital is half empty. So it's going to behave more cationically. That means that in this propagation step, that bond is going to break towards the more substituted carbon. Here's the intermediate that I'm going to get. I got the bromine on the external carbon. No surprise there, since we already drew the product in the first step up here. We knew what it's going to be. And I have the leftover electron, on the more substituted atom, because this is still not a filled orbital. So it's still a partly empty orbital. It still benefits from hyperconjugation, just like a fully empty orbital would in the cation case on the right. Third propagation step, we now have that radical and HBr. So remember, we don't have very much of the initiator around, so we don't really have to consider that at this point. So this and this are doing basically what the initiator did in the first propagation step, taking the hydrogen away from HBr. This gives me the product. So now I have my bromine on the external carbon, the primary carbon, the hydrogen on the internal one, the more substituted carbon. So this is opposite the version I got in the just straight HBr with no peroxides version. And my leftover is the bromine radical, which feeds back into the second propagation step. So this will then continue on and on and on until I've burned through all of my alkene and basically generated all of the product. Sort of. There's a twist to that. Step 3, or type 3, not really step 3, termination. Now, given my generation of being, a teenager in the 80s, I have to say that a certain way. Termination. Okay, so termination is what happens when I put together any two radicals, and they're going to form none by forming a covalent bond. These are high energy species. If they run into each other, then they will kill each other, and they'll have nothing left to work with. So that means any two radicals in this entire process, there are going to be a whole bunch of these, and you can imagine any of them. Basically, none of them gives me what I want. So if I had two of the bromine radicals come together, well, then I've got Br2. Useless. If I have the radical here and a bromine radical, I get a dibromination. Not what I wanted. Not useful. If I have too much of the carbon radical, I could get that hitting another one of those. And then I get something weird looking. I get something with multiple alkyl groups that I didn't want. trying to draw it symmetrically here. And I've also got anything involving the peroxide. So the original initiator could react with a bromine radical, could react with a carbon radical, to give me other additional products I didn't want. So I could get something like this. I could get something like this as termination products that I didn't want. All these are undesirable. None of these are the product I actually wanted out of the reaction. All of them basically kill off two radicals that I needed. If I go back a step here, back to my propagation steps, all of my propagations went one radical to another. So in every step I used a radical, but I generated a different one. In the first propagation, initiator radical, bromine radical. Bromine radical, carbon radical. Carbon radical, back to bromine radical. So I get something to keep the cycle going in every step. Termination, I don't get that. Termination, I got no radicals left at the end, and I killed off two chains that were going forward. So I want to minimize this as much as I can. So very important here, more so than any other type of reaction, must control concentration. Now, oddly enough, we're almost in the perfect time to explain this because we're not allowed to run into other humans anymore in social distancing. Basically, what we're talking about with radicals is we want them to practice the equivalent of social distancing, because if they collide with each other, it's over. No more reaction. So basically, the concentration of any radical species has to be low. That's why we don't have a lot of initiator present. Remember, when I talked about that, I said the initiator would be something less than 5%. Well, the idea there is I don't have a lot of radicals present at any point during the reaction, and that minimizes the kinetics of all of the terminations. The terminations are all second order in radical. The propagations are only first order in radicals. So there can be plenty of alkene present, but as long as there's not much radical present, then I don't have to worry about the terminations. The terminations fall off with a second order, whereas the propagations are only first order. So I have more room with concentration to still have a functional reaction and minimizing the termination steps by lowering that concentration. So this reaction is very touchy about concentration. If I use too much initiator, then I get too much radical, and from there I get too much termination. Remember, every termination kills off two of the radicals that I needed to do the reaction with. So the higher the radical concentration, the worse this reaction is going to work.